Integrated rate laws is going to be the topic of this lesson from my new general chemistry playlist. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also offer MCAT, DAT, and OAT prep as well. You'll find those courses at chadsprep.com. I'll be sure to leave links in the description below. Now, this lesson is part of my new general chemistry playlist. I'm releasing several a week throughout this school year, so if you want to be notified every time I post one, subscribe to the channel, click the bell notification. So there's going to be 3 parts to this lesson, and we'll start by taking a look at some of the mathematical calculations we'll be using these integrated rate laws for. And we'll take a look at half-lives and how they come from these integrated rate laws. And then we're going to take a look at some graphical relationships we can elucidate or determine from these rate laws as well. So let's start with calculations. So first thing you need to realize is that these integrated rate laws are all about calculating concentration changes over time. That's what they do. So now, you might be like, well, why do they call them integrated rate laws? Well, integrated comes from the word integral, as in calculus, if you're at all familiar. Well, calculus is not required typically for a general chemistry class. So if you are in the very vast minority that are on the hook for that, my apologies. I'm not going to actually show the derivation of these integrated rate laws, but they do come from solving a differential equation by taking an integral, by using a little calculus. That's where they come from. I will create a little separate video after this one for those of you that are curious, or if you're one of those very tiny number of people that need to know this. Most of you don't, but I will make a separate video kind of showing their derivation following this one. But for now, just suffice to say, you need to know how to use these equations and what they're used for. They're used to calculate concentration changes over time. So if we look here, you've got an initial concentration, you've got a final concentration after the passage of however much time you're talking about, you've got the rate constant, and you've got time in every single one of these equations, and they're slightly different in how they present themselves. And so we're going to start by just doing a little math here. So the question we're going to take a look at here is for the reaction A goes to B. And it says, what is the concentration of A after 1 minute? So time here is going to equal 1 minute. If the initial concentration is 0.5 molar. And so in this case, the initial concentration of A is 0.5. Let's get a big M on that. Cool. And there's 3 parts to this question. So we're going to do it considering its 0 order, considering its first order, or considering its second order. Typical question, they've got to give you which order it is. So if I said, if I gave you this question and I said for a first order reactant, well, then you'd only be using this equation. Well, we're going to perform all 3 calculations. And again, they just got to tell you which one it actually is on the particular calculation you're doing. And they might tell you that directly. They might say for the first order reaction, or for the second order reaction, or for the 0 order reaction. Or they might do it subtly based on the units of the rate constant. Now, the rate constant for every single one of these is 0.001. At least that's the magnitude, the numerical value of it. But the units are going to be different. We saw this earlier in the chapter where the units of the rate constant are different depending on the overall reaction order here. And so it turns out there was a quick way to remember it, though, is that if you take the exponents on the molarity and the time and add them together and take the absolute value, it will correspond to that order. So in this case, molarity seconds to the -1, well, just plain old molarity is the same thing as molarity to the 1 power, same diff, and 1 and -1 adds up to 0, and the absolute value of 0 is 0. For first order, the units are just going to be time to the -1 power, and in this case, you just add up -1 to 0, and you get -1, and take the absolute value, and you get first order. And then finally, for second order is going to be molarity to the -1 and time to the -1. -1 and -1 is -2, and the absolute value of -2 is just plain old 2, and it corresponds to second order. So pure, just random coincidence, but a nice convenient way of remembering how the units of the rate constant can indicate what order you're talking about here. And so if your professor is in a normal mood, they're probably just going to tell you what order reaction you're dealing with. But if they're not in such a good mood, like their team just lost the Super Bowl or something like that, they might want to take it out on you. And instead of telling you what order it is, they might just give you the rate constant and expect you to figure out what the order is based on the units. So it's much more common for them to just be straight up and open and give you the order, but my apologies if it's the other way around. But we're going to do all 3 calculations just so you can see an example of each. And so if we assume this was a 0 order reaction, this is the equation we're going to follow here. And so the concentration of A is going to equal the initial concentration, 0.5 molar, minus K, 0.001, times time. We got to be careful here. So the units for time in your rate constant and the units for time that you're going to use for t here have to match. And so if the rate constant is molarity per second, well, then time's going to need to be in seconds. And so instead of 1 minute, we're going to use 60 seconds. That way these will cancel. All right, so if we pull out our handy dandy calculators here, we're going to get 0.5 minus 0.001 times 60, and we're going to get 0.44 molar. Okay, so that's for a zero order. If we go for first order here, it's all based on natural logs instead here, and so we're going to end up, and let's just give ourselves a little bit of room here. Natural log of the initial, actually natural log now, A at time t is equal to the natural log of the initial concentration, so natural log of 0.5 minus K, 0.001, and in this case just seconds to the minus 1, and that means time's going to again have to be in seconds. And so instead of 1 minute, we'll plug in 60 seconds. And from here, we'll go natural log of 0.5 minus 0.001 times 60, and we're going to get negative 0.753. And that's the natural log of A, though. And so to solve for A here, again, to get rid of that natural log like we've seen, it's the exponential on both sides. And here they cancel. And you're going to be left with A equaling e to the negative 0.753. So if we figure out what that is equal to, so e to my last answer is 0.47 molar. All right, and finally, what if we were told it was second order? Well, then this would be the appropriate equation to use. And so we get 1 over concentration of A equals 1 over the initial concentration, plus K, which is 0.001, m to the minus 1, s to the minus 1, and once again times 60 seconds. And that way, once again, our s to the minus 1 and our seconds cancel. And in this case, we're going to get 1 divided by 0.5. Oop, that's not that. 1 divided by 0.5 plus 0.001 times 60. We're going to get 2.06. So this means that 1 over the concentration of A equals 2.06. And therefore, A is equal to 1 over 2.06. Now let's see what that is. 1 divided by my last answer. We're going to get 0.4854, and I'll round that to 0.49. Cool. This is kind of how it works. And again, you've got to be told the order, or worst case scenario, you've got to be given the rate constant and be able to figure out the order based on the units. And again, we don't typically make students memorize these integrated rate laws. They're typically provided for you. They're even typically labeled as 0, first, and second. And so we've got to, in one way, either directly or indirectly, tell you which one to use. And then you've got some plug-in and chug-in to do. All right. You might also be given some information about what's called the half-life. So let me get an expression up here for each of these for what's called the half-life, and then we'll do some practice here. So now we've got expressions for these half-lives. Here's the zero order half-life, first order half-life, second order half-life. And first you need to understand what a half-life is. And a half-life is simply the amount of time it takes for your reactant to reach half its original concentration. So that's it. So if you start off with, a 10 molar concentration, how much time would it take to where you've only got a 5 molar concentration left? Or how much time from there to where you've only got a 2.5 molar concentration left? It's always half of what original value you decide to start with. And so that time is characteristic. Now, one thing you should notice, though, is there's something peculiar about the half-life for the first order equation. It is the only one of the three that does not depend on the initial concentration. So notice for the zero order, so the greater your initial concentration, the greater this half-life. And so the half-life is actually changing. As your reactant gets used up, this concentration is going to go down, and your half-life is going to get shorter and shorter and shorter. It's the exact opposite for a second order. In this case, there's an inverse relationship between your half-life and the initial concentration. And so depending on what time point you choose, again, as time goes on, that concentration of A is going to be getting used up. And so whatever you choose, your initial concentration will be a smaller number, and your half-life will get longer and longer and longer. And so for zero order, the half-lives get shorter and shorter and shorter over time. And for second order, they get longer and longer and longer over time. But for first order, the half-life is independent of the initial concentration. And so the half-life is going to be constant over the life of the reaction. So it is only dependent upon the rate constant, it turns out. And it comes down to this lovely expression. So if you take a look at your integrated rate law, you could subtract the ln of A naught to the other side there. And so we could have ln of A minus ln of A naught equals negative kt, but a subtraction of logs can be written as a ratio under a single log term, and so this can be written as ln of A over A naught equals negative kt. And in fact, this is a common way the first order integrated rate law is often also presented. Not just like so, but often like this as well. Now in this case, what's interesting though is that this ratio at the half-life between A and A naught is always going to be a ratio of 1 to 2. If this is A initial, well, then this is going to be half A initial as long as you're at the half-life. And so if we substitute some expressions into here, so at the half-life, we're going to have half of A naught right at that time. A initial is still A initial, and this is going to equal negative K, and the time is the specific half-life time. And if we rearrange this, we're going to get ln of 1/2 equals negative K times T1/2, and we can then solve and see that T1/2 is going to equal natural log of 1/2 over negative K. Well, it turns out that the natural log of 1/2 is going to be negative 0.693, and then when you factor in the negative sign, it becomes positive 0.693, and then again, you've got to divide by K, and that's where this expression comes from. So, and some of you will have to memorize this lovely expression. Some of you will just be given it. I really can't tell you which is going to be the case. That will be up to your particular instructor. But again, the first order is one we spend a whole lot more time talking about the half-life. So, because it is independent of concentration for one, but two, the context in which half-lives most commonly come up is radioactive decay. And all radioactive decay, it turns out, is first order and therefore has constant half-lives. And so if you're doing any kind of calculations with half-lives, more than likely, 90% chance it's probably about first order. Now, if it's about zero order or second order instead, my apologies. Those are going to change over time, and they have to tell you what the initial concentration is. But for a first order, it doesn't matter what that initial concentration is. So let's take a look at some examples of what you might see involving half-lives. Now, we will actually visit this again at the end of this course in a chapter on nuclear reactions. Because again, nuclear decay is all first order decay, and it's all going to follow this lovely set of equations. So, but we're going to kind of study it in that context now. So a couple different ways you can look at this. You could look at this and say, well, what if I started out with 64 grams of some radioactive substance? And the question might be, well, how much is left after one half-life? Well, again, the half-life is the time it takes to have only half as much left. So after one half-life, you'd only have 32 grams left. Well, then how much would be left after a second half-life? Well, then it would be down to 16 grams, and then down to 8 grams, and then down to 4 grams, and so on and so forth. And it just keeps getting cut in half. And if you notice, you might be like, oh, so the rate's constant. No, the rate is not constant. So the half-life is a constant number, but notice during the first half-life, 32 grams disappeared, got reacted. During the second half-life, only 16 grams got consumed. And during the third half-life, only 8 grams got consumed. And so the reaction is slowing down. Only zero-order reactions are going to proceed at the same speed. It turns out first order and second order are going to slow down because as you use up the reactant, well, they're both dependent upon how much of that reactant you have. And so as you have less, they slow down. So in this case, don't think that the constant half-life means that the reaction is not slowing down. It is totally slowing down. Now, let's say I told you that the half-life was 10 minutes for this given radioactive nuclide. And so in this case, we'd have 10 minutes here, 10 minutes here, 10 minutes here, 10 minutes here. And if I just said, hey, radioactive nuclide has a half-life of 10 minutes, how much would be left after 30 minutes? Well, you'd have to be like, well, if the half-life's 10 minutes, then after 30 minutes, it would just be 3 half-lives, and I just have to divide it by 2 or cut it in half 3 times. And so once, twice, 3 times, 8 grams left. And oftentimes, if the time they give you is an actual exact number of half-lives, which is super common, then you just have to know how many times am I dividing by 2 or how many times am I multiplying by a half. And so essentially, you're just dividing it by 2 to the n power, where n is the number of half-lives. So I personally just like to kind of represent it in just this fashion and work it out. Divide by 2, 1, 2, 3 times, 8 grams left. Life is good. Now, they could give it to you in grams like this. They could also do it in terms of, like, say, percentages. So you always start with everything that you have. So you start off with 100%. And so the question might be instead, what percentage is left after 30 minutes? After, again, we'd figure out that that's 3 half-lives if the half-life is given as 10 minutes. Well, after the first half-life, you'd only have 50% left. After the second half-life, you'd have only 25% left. After the third half-life, you'd have 12.5% left. That's what that question would be asking. If you went further, it'd be down to 6.25%, so on and so forth. Or instead of asking you the absolute mass that you've got left or the percentage you have left, they might ask for the fraction you have left. Well, again, you initially start with all of it, which just is 1. And after the first half-life, you'd have half of your sample left. After a second half-life, you could have half of the half, or 1/4 of your sample left. And after a third half-life, you could have half of the fourth, or 1/8 of your sample left. And 1/16, 1/32, so on and so forth. You just keep multiplying by a half. And they could ask it in any one of these contexts is pretty common. Now, if we want to make this a little more challenging, instead of actually telling you that the half-life is 10 minutes, I could have given you the K value instead. So in fact, let's do this. So if I get 0.693 divided by 10, so I could have told you that the K value was 0.0693, and then you would have plugged in 0.693 over 0.0693 and got a half-life of 10 minutes. And so instead of giving you the half-life directly, I could give you the rate constant and then expect you to figure it out and then do the same kind of basic calculations here. If I really wanted to make this difficult, instead of giving you a nice round number and said, how much is left after 30 minutes? I could have said, well, how much is left after 27 minutes? Well, that would suck. Because here's how much is left after 20 minutes. Here's how much is left after 30 minutes. 27 minutes would be somewhere in between. And you can't just quickly determine it in the same way we did when it was a nice round number or whole number of half-lives. Now, we know it'd be, say, somewhere between 16 grams and 8 grams and probably closer to 8 grams, or somewhere between 25% and 12.5%, but probably closer to 12.5%. But what you'd ultimately have to go back and do is go back and use the first order integrated rate law to figure out how much is left, being given the initial amount and the rate constant and the amount of time that has passed. And that would suck, but it would be just the same kind of calculation we did earlier using this integrated rate law for a first order reaction. All right, last but not least, we've got to talk about some graphical relationships that we can look at for each of these different orders. And you've got to understand how to get a straight line for each of these. And it has kind of some laboratory related relevance and stuff like that maybe you'll see an exercise on in the lab, maybe you won't. So, but you do got to know these graphical relationships for the lecture as well. And so if we go back and take a look at these equations here, so we're going to match each of these equations, these integrated rate laws, with up to the slope-intercept equation of a line. In fact, I'm going to get rid of these half-lives. They're just going to get in our way. Slope-intercept equation of a line, y equals mx plus b. In this first one here, we're going to do y equals b plus mx. Second one here, y equals b plus mx. And this last one here, y equals b plus mx. And so you might be like, wow, why'd you do b plus mx instead of mx plus b? Well, if you got to look at what your variables are in this equation. So you've got the concentration of A you have now, and that's changing over time. And then time is changing. Those are your variables. The initial concentration you started a reaction with, that's fixed. It just is what it was. You know, whatever it was, that's what it was. It's not changing. The concentration is changing, but the amount you started with is not changing. And then K is a constant as well. So these are constant depending on whatever initial conditions you started with, but it's the concentration over time and time itself that are changing. We call time the independent variable, and the concentration of A here would be the dependent variable, and you always make the independent variable X and the dependent variable Y, and that's why we kind of arranged this the way we did. And so in this first one here, we can see that on the y-axis, you want to put the concentration of A, and on the x-axis, you want to put time. And so in this case, you're going to get a graph with a negative slope, and that slope here is going to equal negative k. And if we cared, the y-intercept here would be the initial concentration of A. Now cool, if you plotted A versus time for a first order reaction or a second order reaction, it would not come out as a straight line. It's not a linear plot. So the study guide, I put the 3 different plots that are relevant, as we'll see, for all 3 for every single order so that you can see that only one of the plots comes out linear. So in this case, this is a logarithmic relationship and this is an inverse relationship, and those aren't linear. They wouldn't come out as straight lines. And so if you want to come out with a straight line, you got to do a little different plot. Now for first order and second order, again, I've matched up the integrated rate laws here with the y equals mx plus b slope-intercept equation of a line. And notice that always lining up with x is time. Your independent variable time is always going to go on the x-axis for every one of these. Now, one thing to note, and be very careful, I've seen professors get really tricky on this. On the x-axis is time, and time is represented by a lowercase t, not a capital T. A capital T means temperature, and that's not relevant here at all. It's got to be a lowercase t, so be super careful with that. But we see on the y-axis, it's not just the concentration of A after a given amount of time, it's the natural log of the concentration of A. That will plot on the y-axis. And once again, this is going to give us a straight line. And the slope is going to equal negative k. And so it's a negative slope yet again. And that slope is negative k. In fact, this is how we often determine it. If I know a reaction's first order, I've determined from some experimental data that it's first order, I'll often plot the concentration of A over time and get this graph. And then I'll use a scatter plot to kind of get the best fit line to this and use the slope of that line to get the k value. If the slope came out to like, negative 0.05, well, then I'd know that k was equal to 0.05. So that's kind of the way this works. So these plots are often useful in the lab for actually determining rate constants. All right, and finally, the last one here. So I can see that, again, time lines up with x from the slope-intercept equation of the line. But for the y-axis, I actually want 1 over the concentration. And in this case, this is the only graph also. If you look here, the slope is not a negative number, but a positive number. So it has an uphill slope, and that slope is going to equal plain old k, which I'll write as positive k. And so you should recognize some differences here. So one, you want to get a straight line. That's what we want for the laboratory. For zero order, it's got to be concentration versus time. For first order, it's got to be natural log of concentration versus time. And for second order, it would have to be 1 over concentration versus time. And again, only one graph of these 3 possibilities ever comes out linear. If you have a second order reaction, then the plot of 1 over concentration versus time comes out as a straight line. If you happened for a second order reaction to make either one of these graphs of A versus time or ln A versus time, they would not come out as a straight line. Only the relevant plot for a given order, only one of those graphs comes out as a straight line. In fact, we often use that as a test. Oftentimes, if I don't know if a reaction is 0 first or second order, I make these 3 plots and then figure out which one is the straight line and use that to determine which order it was. If the straight line comes out as ln A versus time, well, then I knew I just figured out that reactant was first order. So that can be used as well. You should also recognize that for zero order and first order, the slope of the line is negative. So, and that's from that negative sign right there in the equation. Whereas for the second order, the slope of the line is positive uphill from the positive sign in the equation right there. And these are kind of some of those graphical relationships you need to understand. What they might do is give you, 4 graphs and say which one corresponds to a second order reactant, and you'd have to identify this as the correct one, and these would be incorrect. And if they really want to slip you up, the other incorrect one they might give you for a second order plot is they might give you 1 over A versus time, but give you a negative slope. And again, for a second order plot, you would get a straight line with 1 over A versus time, but it would have a positive slope, not a negative slope. And this would be another incorrect answer choice. Now, if you found this lesson helpful and want to support the channel, that thumbs up button, one makes my day, but 2, lets YouTube know that they should be sharing this lesson with other students as well. And if you are looking for practice problems for kinetics or anything else in general chemistry, check out my general chemistry master course. It includes over 1,200 practice questions, including practice final exams. A free trial is available. I'll leave a link in the description. Happy studying.